Given k lists of integers, each already sorted in non-decreasing order. Find the smallest range that includes at least one number from every list. A range is smaller when its span is tighter, and ties go to the smaller start. The goal is that smallest covering range. Example 1 gives 3 sorted rows. We need one value from each row that all fall inside the tightest window. We take 24 from the first row, 20 from the second row, and 22 from the third row. Together they span from 20 to 24, a window just 4 wide, which is the smallest range that covers every list. Example 2 shows 3 identical rows. Since the value 1 appears in every row, a single point covers all lists at once. The smallest range is 1 to 1, a window of width 0. Before we write any code, let's understand exactly what this problem is asking. Imagine each sorted list is a distinct team color, red, green, and blue. Our goal is to drop a single net onto the number line that is wide enough to capture at least one number from every single color group. We want to find the absolute tightest, smallest net possible that still contains all 3 colors without dropping any team. If we try to find our optimal net by blindly combining numbers from all lists at random, we are instantly paralyzed by the sheer volume of choices. Testing every combination creates a chaotic web of intersecting spans that breaks our performance. We need a coordinated strategy to pinch these numbers together systematically. Let's bring order to this race. Because the lists are already sorted, we start by placing a tracking pointer at the absolute beginning of every single list. Right now, our pointers are resting on 4, 1, and 5. This gives us our very first valid baseline window. It stretches from our current minimum of 1 to our current maximum of 5. We evaluate this initial window. It covers a 1, a 4, and a 5, meaning every single color is successfully represented inside our net. The span of this range is 5 minus 1, which equals 4. We record this range on our leaderboard as our current best target to beat. Now, how do we shrink this range? To make a range smaller, we either have to bring the maximum down, or pull the minimum up. Because our pointers can only move forward through these sorted lists, our maximum can never decrease. The only way to optimize this range is to find a larger replacement for our bottleneck. We must greedily slide the pointer holding our absolute minimum value. We advance our bottleneck pointer. It leaps forward from 1 to 20. Instantly, our window state recalculates. Our new minimum steps up beautifully to 4, but our right edge explodes out to 20 to accommodate our new addition. Our active range is now 4 to 20, a massive span of 16, which fails to beat our champion score of 4. To keep this race running at lightning speed without manually searching for the minimum element every single time, we use a min priority heap. The heap acts as a dynamic sorting scale. It continually pushes the current bottleneck right into our extraction tray, while we effortlessly maintain a single variable to track the maximum ceiling. We pop, advance, and reinsert in one smooth, continuous engine rhythm. We continue this high-speed race until any single pointer runs completely out of numbers and drops off the edge of its list. The moment a single list is exhausted, the race terminates instantly. Why? Because any future window would be completely missing an element from this empty highway, making a valid net impossible. We lock the gates, pull our ultimate champion range of 1 to 5 from the ledger, and finish our sweep. We initialize our execution engine by seeding our min priority heap with a tracking tuple from the very first index of every single list. Each tuple binds the raw value, its source list index, and its element column pointer. As these load, we simultaneously track the largest value we've encountered so far, establishing our initial max ceiling at 5. Before we enter our main processing cycle, we take a snapshot of our initial configuration. We peek at the top of our priority scale to find our absolute minimum, which is 1, and pair it with our global maximum ceiling of 5. This gives us our baseline champion range to beat. We initiate our core contraction loop, which runs continuously as long as every single list is represented on our scale. We pop the absolute bottleneck off the top of our heap. This element, 1, tells us exactly which list is dragging our window backward and must be advanced. At the start of every extraction, we check if our active window is tighter than our previous champion record. We compare the distance between our current maximum and minimum against our leaderboard. If the new span is strictly smaller, we update our victory coordinates. Since our initial span of 4 simply matches our current record, the ledger parameters hold steady. Now we must find a replacement for our evicted bottleneck. We look up the source list index of our popped element, which points us to list 1, and increment its element pointer to the next index. We uncover a 20. Because this 20 is larger than our old ceiling of 5, our global maximum tracking variable instantly updates to 20. We lock this new candidate into a tracking tuple and insert it directly back into our priority scale. The heap automatically adjusts, forcing our next absolute bottleneck, up to the extraction tray, preparing the engine for the next iteration. The engine sweeps forward until a pointer attempts to step past the final index of its list. The moment we look for a replacement element and find an empty highway, our guard condition fails. Because it is mathematically impossible to form a valid range without representation from this exhausted list, the loop terminates instantly. With the search space safely exhausted, we break out of our engine structure. We extract our final, optimized boundary metrics from the ledger board and return our definitive answer array, 1 to 5. Our multi-pointer harvest is complete. Time is nlog k. Across the whole run, every value from every list is pushed onto the heap and popped exactly once, and each of those heap operations costs log k, where k is the number of lists. Space is order k, because the heap only ever holds one pointer per list, so at most k entries live in it at a time. We define our routine. It takes the k-sorted lists and returns the smallest covering range. We start with an empty min heap and set the running maximum to -infinity. We loop over every list by its index. From each list we push its first value, tagged with its list and column, folding that value into the running maximum. The heap's smallest value paired with the running maximum gives our first candidate range. We keep contracting as long as every list is still represented on the heap. We pop the current minimum, the value dragging our window's left edge. We check whether the gap from this minimum up to the running maximum beats our best range so far. If it is strictly smaller, we record the new champion coordinates. We look at the next column in the list that owned that minimum. If a value is waiting there, we read it. We update the running maximum in case this new value is larger. And we push it back onto the heap so every list stays represented. If that list is exhausted, we skip the push and the loop ends on its own because the heap no longer has k entries. Finally we return the smallest covering range we recorded.